back on and recording back on. Okay, so just before the break, I said that the shape functions is everything, and they are really everything. With the help of the shape functions, you can describe the stiffness matrix that tells you how is that you can describe the deformation within the one element. Now, shape functions can be also used to describe inertial properties. That's a mass matrix. And how it happens is that you simply take the shape functions, as they are, and it's transposed, and this is you multiply with the density of the material density. You integrate that over the volume of the element. That's it. These kind of things are very mechanical, and again, with the help of the symbolic math tool, it should be no problem to do it. Now, for that beam element, the stiffness matrix, if you're using the method that is based on these shape functions, it can be written as it is shown here. So again, it's a 4x4 matrix because of the 4 degrees of freedom in my one element. Now, next, I'm going to just give you a few observations that I'm sure you're already familiar with. These are related to nature of, again, a little bit like how is a finite element method. Just because the finite element method is so different than multi-body system dynamics. As I explained, finite element method requires that there's a lot of elements that is describing your structure. So your structure should have enough elements. How the elements are then treated in finite element method in order to make a structure. That's where the finite element method is very different than multi-body system dynamics. And to explain that to you, I have here two elements, A and B. Both are symbol elements that are like spring elements. Both elements consist of two nodal degrees of freedom, and each one of the nodal degrees of freedom, they have just 1 degree of freedom, so they can move back and forth, nothing else. So here is my first node, here is my second node, and then when I'm moving to my element B, I have another set of 2 degrees of freedom. Here's my first degrees of freedom, and here's my second. And now in a finite element method, what I'm doing when I'm assembling them to describe the entire structure is that I'm saying that these 2 nodes will share the nodal degrees of freedom, so they will be united. So they will be united such the way that the displacement 2 and displacement 3 will be all the time same. What that means in an element level, well, it means that if this is a stiffness matrix for my first element, and this is my stiffness matrix for my second element, when I'm uniting these degrees of freedom to be same, it means that the the stiffness matrix, the one that is describing the behavior of the structure, will be constructed such the way that my first element will be here, and my second element will be here. This is where they're overlapping, and this is the displacement that is associated to 2 and 3. So this is the behavior, and this is a pattern that you're combining the structural matrices for stiffness and inertia as well. Now, boundary conditions, well, depending what kind of boundary conditions you're dealing with, but in a simple linear cases, you can simply take if you say that this spring structure that is showing here will be attached to crown from this end, you can simply go and eliminate the corresponding rows and columns from your stiffness matrix. But that really depends on what kind of boundary conditions you're dealing with. But this node here is eliminated from the stiffness matrix, and what I just left here as a 1 is a diagonal component to be able to invert this. Now, but this is something that is a little bit off from the scope of this class. And the final note that is also a little bit off from this class or this course is that element orientation can be accounted by something that is called transformation matrix, and the transformation matrix accounts the orientation of finite element. And that's what is make it possible to combine element like this and element like that and make whatever structure you want, trust element or whatever you want. How it goes in details? It goes in details such the way that you combining global degrees of freedom and local degrees of freedom, and that you can make it happen with this transformation matrix. We are not going to take a look at that in details because these are all element dependent, and it depends on what kind of element you're dealing with. But now, something more interesting than that is this. And if you're interested in those details, there's a huge amount of material that is available in YouTube and in literature. You can go and look at the details about the transformations, about how to make a system matrices, structural matrices, and so on and so forth. But once you have accomplished everything, once you have assembled inertia, once you have assembled the stiffness, once you have described externally applied forces, then finally your finite element equations of motion, and this is now equation of motion, looks like this. This is how it reads. So simply what I have here inertia forces that are described with respect to nodal degrees of freedom. All right? Mass multiplied by acceleration. Then I have here my displacement, which is a stiffness multiplied by stiffness matrix multiplied by stiffness. So this is elastic forces that are trying to put the structure back to its undeformed configuration. Elastic forces. And then here I have my externally applied forces. And those are the forces that will cause deformation. That might cause a deformation. Of course, it could be rigid body motion too that they are causing. But generally speaking, they typically cause a deformation. Now, what I need, again, now we need to go back to this floating frame reference formulation, and like origin of this study, and origin of this story. Everything started because of this. In a floating, let me make this. No, this is not the case. So let me make this more readable. This. Okay. In a floating frame reference formulation, the kinematic reads like this. Another mistake. This one. Okay. So here is my translation of my reference coordinate system. Here's a rotation of my reference coordinate system. This is where the particle is located on its undeformed configuration. And this is description of deformation. This is exactly what I'm about to get from the finite element method. So this one here, vector u bar f, even though that the notation is inconsistent, is exactly this. So this is what I'm solving here. This is what I'm after all the time. Why? Because this gives me how is a nodal displacement, and with help of the nodal displacement I can get the displacement of any particular location I want with help of shape functions. All right? Now this is how can I solve this equation of motion, this one that is shown here. And this is the method that we cannot use in practical life. Now why is that? Well, that's simply because if you think about the dimensions of this equation, typical finite element model consists of, say, 100,000 degrees of freedom, easily. It could be 500,000 degrees of freedom. 10,000 degrees of freedom is very, very typical. And now that's a big mismatch, because think about how many coordinates I need to describe my reference motion. This one and this one. I need 6 or 7 max, depending what is rotational parameters that I'm using. But let's say that I'm using 6. That's how much I'm describing my last relative translation and last relative rotation. And then I'm using 100,000 degrees of freedom to describe the deformation. No good. 6 versus no good. No, you cannot put these two things in a one room because they don't fit in the one room. You have to do something to this one. You have to make them smaller. Otherwise, you cannot solve these together. And again, let me emphasize this. You have to solve this every single time step. So it's not enough to solve 6 every time step and then this 100,000 every now and then. No, that's not all right. But you have to solve them every single time step. That's why we have to do something for this 100,000. What we will do is a modal reduction. Modal reduction is something that we're going to take a look at the next. Okay, so here's a same explanation, pretty much the same explanation that I just did. But now how is this modal reduction? How that is going? This is where you need to put the full attention to me, because this is going to be, first of all, very difficult concept. It's very theoretical concept. And at the same time, it's very useful concept. Okay, and also you need to pay attention when I'm saying modal and nodal. Because of my accent, can you recognize the difference? Nodal, modal. Is it all the time same? Because it's not. It shouldn't be same. These are two different stories. So you recognize the difference? Great. So let's take a look. Now, what we will do to solve this mismatch, to solve this monster that is a size of 100,000, with this tiny guy that consists of 6, how to make them roughly in the same level, we're going to jump from nodal decrease of freedom to modal decrease of freedom. Modal decrease of freedom. Clear? Because why is this so important? Because this was some years back. I was explaining this in Denmark, and end of my class, and it was a full day class, I recognized that people don't see the difference about nodal and modal. So it was all waste of time and effort. So that's why I'm emphasizing modal and nodal. Clear? If you don't know which it is, raise your hand and then I will repeat it. Okay, now, what we will do, let me try to explain this to you. In order to explain this, we have to look at a cantilever beam. I have here a cantilever beam like this. And I say that this cantilever beam consists of let's say this is subjected to boundary conditions, so it will disappear. So its displacement will be 0 no matter what. But let's say 1, 2, 3, 1, 2, 3, 4, 5. 5 nodes. And let's say that each one of these nodes can have 2 degrees of freedom. And these 2 degrees of freedom are such that each one of these nodes, they can move to global y direction, back and forth, and then they have a rotational degrees of freedom. So, like this. So, a total of how many degrees of freedom? Each one of them will have 2 degrees of freedom, and we have a total of 5 nodal coordinates, 5 nodal locations. Excuse me. So how many in total? 10. So 10 in total. Correct. 10. Now, if you're going to solve this by using this method that I explained in a previous slide, it means that you have to deal with the 10 unknowns. 10 unknowns. There's an alternative way, because what we could do is that we could take a look what are the possible deformation of entire structure. Okay, the possible deformation of entire structure means that there is a behavior pattern again. Not this time about the one single element, but entire structure. Behavior. Possible behavior. Okay? Possible behavior we can get by computing or conducting an eigenvalue. We can get back to this eigenvalue, but we can think about the natural frequencies and corresponding natural eigenvectors of this structure. So if looking at how is the vibration of this structure, probably the lowest possible frequency and associated deformation is something like, let me change the color because this is really important, it's something like this. Roughly, you get an idea. Okay, what is this? This is one possible way that the structure can deform, entire structure. And now let's look at this. That's the way that I have a deformation where each one of the nodes will move according to this behavior pattern, like shown here, and they will rotate according to this behavior pattern. How much? How much this will contribute? How much this will affect? I don't know. This is my question mark. And the question mark ID 1. All right? Then I have another behavior pattern. I can look at what is another natural frequency of the structure, and it's probably something like this. This is another possible way that the structure can deform. And this is how much, the way that they can, the nodal degrees of freedom can move with respect to each other. But how much? I have no idea. But this is called question mark 2. Then I can have another and another, but how many in total? 10. Because I have 10 degrees of freedom in the structure, so I can have 10 different ways that the structure can deform. Each one of them are associated to question mark, and the question mark is called amplification. Later, we will call these as a modal degrees of freedom. And now what we will do is that we're going to leave this nodal degrees of freedom and we're going to start looking at the ways the entire structure can deform and perform. And then these ways will be, each one of them will be associated to amplification factor, that is my modal coordinates. Now in this particular, I need to repeat this number of times because this is really complicated. Even though that I'm sure you heard this story like a million times before, but still is really, really complicated to understand in details. And I would like you to understand this in details. Yes? Okay. Now let's breathe first. 3 times, really deep. Think about something pleasant like good winter weather. No, summer weather, of course. 2nd time. Final. Okay, so let's get back to this nightmare. Now, so here I have a structure that consists of 10 nodal degrees of freedom. So let me try to make this clear. So 10 nodal degrees of freedom. What this means for us? This means that the structure can deform in 10 different ways. 10 different ways. What are these different ways? Well, we can get these different ways by using an eigenvalue analysis, which meaning that we are looking at the natural frequency of the structure and corresponding deformation modes. How that goes in details, we will get back to that. Now we have 10 different ways. How much each one of the ways will make a contribution to final deformation? I have no idea, but let me find it out. And this is where I'm moving from my nodal coordinates to my modal coordinates. And modal coordinates is my, how much each one of these assumed deformation will contribute to final deformation. Now the beauty of the method is this, that I have here 10 degrees of freedom. So if I would deal with the finite element method with the 100,000 degrees of freedom, how many different ways I can extract from that finite element method, finite element model? What's the number that I said in the beginning? 100,000, right? How many I can get it out? 100,000. So 100,000 different ways. How many of them are really important in terms of dynamic performance? Well, each will contribute a little bit, but typically they are not equally important, but some of them are more important than others, and some of them are very insignificant. Some of them makes almost like no contribution whatsoever. So what I can do is that I can actually ignore some of the deformation mode without significant loss of accuracy. And this is exactly what I'm about to do here. So from this on, I'm not planning to use these 10 different ways that the structure can deform, but just say 2. Of course, it's not going to be same level of accuracy, but how much do I need to compromise in terms of accuracy? Not so much. Not so much. Why? Because it's known that if I have here like this 10,000 different ways that the structure can deform, and if you think about the natural frequencies associated with them, some of them will be associated with very high frequencies. Maybe they don't make much of a difference in terms of multibody dynamics. And that used to be the practical case. Okay, so that's how it goes. So, now what I will do is that I will look at these different ways that the structure can deform by using or conducting an eigenvalue analysis. And now comes super important things, because eigenvalue analysis is only telling you the inherent nature of the structure. It's not about the final responses. It's just looking, okay, how is the structure itself? It's not an absolute value of any kind. It's just a behavior model, a behavior way of how the structure can behave, nothing else. How can I conduct an eigenvalue analysis? Well, I'm going to go and take a look at my original equation of motion, this one here. And I'm going to neglect externally applied forces. I'm going to set them to be equal to 0. This is already telling you that I'm not at all looking at the responses, but I'm just looking at how is a feature of the structure, because I'm only what is left is this side of the equation. It's only half of the story. Another half, I don't care, because I'm looking only like how is its behavior model. Okay, so how it goes then? It goes like this. I have here my inertia plus elastic force is equal to 0. And when you have an equation like that, it's known that solution for this kind of equation can be extracted or can be written as it is shown here. So I don't care about the mathematics. It's just that the mathematicians are able to tell that for you. Now you go ahead and substitute that information here, and this is how your equation reads. And now you have something that you got new players in the game, so you have here omega power 2, and then you have a vector. These ones will be very important for us. What we're going to do is that we're going to look at these equations. That's the way that we can first look at this part of the equation, and we set that to be equal to 0. How can we can make that happen? Oh, hold on. We can make it happen by simply taking determinant of this part of the equation and then solving omega from this equation. It gives you the eigenfrequency of the structure. Then you can take the solution one at a time and substitute this equation that gives you the way structure is behaving at that particular eigenvalue. We're going to look at the examples in a second, but that's how it goes. Now, let me ask you this, just to check if you have been listening to me at all. Now, a finite element model shown in this picture here consists of n number of elements and n number of degrees of freedom. The model can be used to solve question mark number of eigenvalues and eigenvectors too. My question is, how many different ways this finite element model deforms? Options are n number, m minus n number, m plus n number. How about the different ways that the structure can deform? Let's take a look. Let's check that. So, next. Okay, so let's go back here. So I have here a finite element model that consists of n m number of elements should be S here, and n number of degrees of freedom. The model can be used to solve question mark number of eigenvalues. It's equivalent to say this model has a certain number of different deformation modes. What is this number? Is it going to be m, n, m minus n, m plus n? How many different ways? Is it too simple? By the way, what kind of candies you would like to get next week? Chocolate or salty candies or no salty candies? Salty candies? Any preferences? No preferences. Okay, so then I will surprise you. Okay, so how is your answer to this question? Here. So I guess that the trick that some of you are using is that I realize that for some reason this Socrative is allowing you to come and enter your answer after I release the correct answer. So I need to find a technical way to make, to somehow prevent that to not to happen. I don't know how this is, how can I do it, but for sure I need to find it out. Because obviously it's either one of you or online participants that are just waiting until I'm releasing the correct answer, and then they will enter the answer. So what I will do next is that I will show the correct answer, and immediately after that I will close the questionnaire. So that option is not available today. So enter your answer, and then when I'm saying now, I will show the right one, and I will close the whole deal. Okay? All right, so now let's look at something else. So I notice that we don't have much of a time anymore, but remember what this eigenvalue, eigenfrequency, and eigenvector, what those means. Those are really important to understand, because otherwise, you will be lost rest of the course. So the eigenvalue means that if you introduce the externally applied force in the same frequency than the natural frequency, then the system vibrates and the amplitude will get increasingly bigger. And theoretically, they will go to infinity. So there's nothing to stop that. In reality, they cannot go to infinity, but that's what it means. So let's look at a couple of videos to give you better understanding. What is this natural frequency and associated deformation modes? And that's right after these animations. We're gonna go and look at the Socrative, and then we will get back to this next week.
A 1 degree of freedom mass spring system has one natural frequency and one vibrational mode shape. The mass oscillates back and forth, or in this case up and down, at a frequency that depends on the inertia, or mass, and elastic, or stiffness properties of the system.
I will use a little bit of...
A 2 degree of freedom mass spring system has two natural frequencies and two mode shapes. In the first mode shape, first frequency, the two masses move in the same direction at the same time, basically looking like a 1 degree of freedom oscillator.
Now, let's go in the beginning. So first, what I will do is that I have this system. This is a system that consists of
a 1 degree of freedom mass spring system has one natural frequency and one vibrational mode shape. The mass oscillates back and forth, or in this case up and down, at a frequency that depends on the inertia, or mass, and elastic, or stiffness properties of the system.
Okay, so let's get one more time from the beginning.
A 1 degree of freedom mass spring system has
1 degree of freedom. How many different ways it can deform? One way. And this one way we can look at by checking how is an eigenvalue and corresponding eigen vector of the structure, which is just the one way.
There's one natural frequency and one vibrational mode shape. The mass oscillates back and forth, or in this case up and down, at a frequency that depends on the inertia or mass and elastic or stiffness properties of the system. At 2 degrees
of freedom, how many different ways? 2 ways. So there is a rule of thumb. Okay, so let's take a look at that.
Freedom mass spring system has 2 natural frequencies and 2 mode shapes. In the first mode shape, first frequency, the 2 masses move in the same direction at the same time, basically looking like a 1 degree of freedom oscillator. In the second mode of vibration, the 2 masses oscillate in opposite directions, one going up while the other one's going down. At the very center in between the 2 masses is a node, a point that doesn't move at all.
Okay, 3 degrees.
A 3 degree of freedom mass spring system has 3 natural frequencies and 3 mode shapes. In the first mode shape, all 3 masses move in the same direction at the same time, with the center mass moving slightly farther than the outer 2.
Okay, then comes next. Hold on.
In the second natural mode, the center mass is stationary at a node point, while the 2 outside masses move with opposite phase in opposite directions.
One more. Can you guess how it is, the one more?
In the third natural mode shape for the 3 degree freedom system, all 2 masses move in the same direction at the same time, but opposite the inner pair.
4 different ways.
In the fourth mode shape, every other mass oscillates at a different direction. There are 3 nodes, one between every pair of masses.
Okay. Now, this is where we're going to end today. And we will continue from that on next Monday. And this, again, let me emphasize, this is super important in terms of not just your midterm exam, but your life. It is really, really critical. So I'm going to go slowly. I'm going to explain this in a way that I know that this is ridiculously slowly for you because you figure out everything a while ago, but you don't care about that. Because myself, I want to really learn this in details. So let's go this slowly on Monday, and let's look how we can use this modal reduction, because it gives us really important features that you can use, not just in the multi-body dynamics, but many other courses here in LUT. Okay, now let me close the recording because the streaming, hold on. I want to use this one. Where is it? What happened? Here.